Okay, so setting in just a little bit of context here, I'm going to talk about roughly where we are today. We can skip over this first part since we're losing a bit of time here just to...
Just press it. I don't want to plug it in and mess it up.
Yeah, sure. So we have a lot of optical cases. I'm going to focus specifically on our data center architecture. We have multiple data centers within a region. We have resilience within a region. But the interesting area for us where we're really pushing on is in terms of the data center optics at the next level down. So if we looked at our networks, which were kind of referenced to earlier, they're pretty conventional. It's a three-stage CLO going from a traditional TOR to an end-of-row switch to a data center switch at the top level. And what we're doing there today, we can optimize the interconnect at each different level. So we're optimizing. So we're still using copper for that last level interconnect from the tier 0 switches to the machines. We've got active optical cables because they're the most cost-effective for the in-row interconnect. And then we're using parallel single mode for what we would call the short reach data center, which is in the sort of 150 to 200 meter range. And actually, we stretch some of those to about 600 meters in some particular cases. But for all intents and purposes, maybe 250 is about the right kind of max on that. And it was kind of mentioned that we were a little bit behind the curve in terms of adoption. One thing that's a little bit different, major real difference in the architectures between some of the cloud providers is whether or not you make extensive use of a back-end network. So for us, for all our high bandwidth use cases in ML and HPC, we actually have a completely separate network for implementing those. And the rationale for that is generally, these are high value, very expensive nodes. We don't want them to be choked at all by the network bandwidth. And also in those use cases, we have less concerns about multi-tenancy and being nice to your neighbors. So our architecture is very much driven by having these separate networks which we can push to very high levels of utilization. And when we're using Ethernet in those spaces, we can push Ethernet to very high level, to the sort of 80, 90% utilization, which would be very hard for us to do on a shared front end network. Now, from the point of view of adoption of new technologies such as CPO and more advanced optics, that gives us some interesting opportunities because whereas if we want to deploy those technologies in our front-end networks, we really need to make sure that we have multi-sourcing in place. We need to have technologies from multiple vendors and multiple interop. We have, in the slightly more limited use cases of the back-end network, we have more opportunity potentially to trial new technologies. Now, the one proviso there is that, you know, we're the plumbing department, basically. So you can never bring a technology into those networks and risk being in the situation where you can't deploy your new compute hardware because the network's not there. So even although those back-end networks are slightly more flexible as being used as targets for advanced technologies, we still have to remember that the key thing is to be able to land the machines. So I think it's all been very well referred to, and we can catch a little bit of time here by not overemphasizing the power stuff, except to say that it hurts us in multiple places. It's clearly a TCO hit, but it also is a hit in all sorts of other places in that if you look at the way that our switching is distributed around different parts of our infrastructure into regional switching gateways and things, there are places where we're struggling to increase the bandwidth because we don't have the power provisioned in those places. And you know, for the ML machines, that tends to be newly provisioned facilities, but we also have a requirement to upgrade networking at our existing facilities, and there we can potentially be quite tight in terms of power. And if you're spending more power on your networking, that takes away from what you can deploy to your actual useful compute. So the sort of disruptive technologies that we're interested in, obviously here we're all talking about co-packaged optics. There are some other interesting things that can be going on that potentially could deliver power savings. And then in the network architecture itself, we can do more things there to potentially bring down the power. And one thing that we're particularly interested in is whether the combination of co-packaged optics and the new generations of very high radix switch would allow us to collapse the number of tiers and go from the sort of three-stage close that we're using to fewer stages. We'll take a little bit of a look at that later on. It was mentioned earlier in one of the questions, should we be doing something simpler? There's definitely ways that we could look at doing that. We already have a level of specialization to these hyperscale switches where they have simpler routing pipelines and are more efficient. We could look at going in that direction. But it has to be said that some things are going in the opposite direction in terms of also wanting to put things like in-network compute into the switches, so that's taking us back in the other direction. And there are some disruptive things coming in terms of how we actually want to deploy and package our machine in terms of liquid cooling, and optics is going to play into that because the introduction for things like immersion cooling will intersect with the similar sorts of dates that we're wanting to introduce optics. So we think about where co-packaged optics could make the biggest difference to us. We can think probably because we're pushing up bandwidth density and bringing down power, the most important place for them to land is in terms of switches. And from our perspective, looking across all our switching technologies, we can roughly classify them as three different sorts of switches. So we've got the conventional Ethernet networking switches, and then potentially switches that are more optimized for low latency applications, and then coming all the way to switches used for disaggregation, potentially for switching between CPUs and memory complexes, and they're driven by different sets of constraints. So they're all interested in pushing down the power, but some of them are more willing to compromise in terms of latency than others. So typically, we can tolerate a few hundred nanoseconds of effect latency potentially in the Ethernet space in a way that would not be possible on the memory disaggregation case. So if we look at what CPO might give us, we tend to focus on the power, but there's a lot of other potential advantages there. Latency, we spoke about. The latency story for Ethernet is just trending in completely the wrong direction. We've got advanced signal processing at multiple stages between the switch, the transceiver on the wire. We've got more and more complex effect coding. So we're at the point where we might be seeing 400 nanoseconds or so, which is equivalent to 80 meters of cable. So you're spending more time in your FEC than you are actually going along the wire. So speed of light is getting a bit of a bum rap in terms of who's causing the latency issues. So very promising in terms of those that right-hand set of switches that I described, the disaggregation switches, that potentially we have a way there to have very low latency optics. The other really interesting one for us is coming out of the co-packaged optics debate is really reliability. So as we move to co-packaged optics, I think one of the big challenges is it's going to change the model of what our field repair is. So we're going to be swapping potentially a whole switch unit. We want to do that less often. Potentially, CPO is going to deliver something more reliable because there's less connectors, less things to go wrong. But when we actually have to do the swap, it's going to be a much bigger thing, and that's going to have cost implications to it about how we deal with those more complex FRUs. So a little example of how we might use large switches. Typically, if we took our middle of row switches today, they'd have top of rack switches below them, copper interconnect, and potentially going to CPO, we could imagine direct fiber connection to the machines, potentially taking a four-way optic and splitting it 4 ways to go to each of 4 different tiers. And this comes to a point where CPO is not just it's not just a pure TCO play, because this is actually subtly changing the reliability architecture. So now we've got one good thing, which is that our failure model is now if we lose a switch, we're dropping only 25%. So that's pretty much in line with the traditional front-end network that you guarantee 75% provision. So you don't immediately have to start draining workload off those if that's in a front-end network. But the bad thing is that the blast radius of that is now many more CPUs. So the blast radius for losing a single switch is now maybe a few hundred CPUs. That's probably, if we think that we can live with the change in the reliability model for the individual nodes on the front end, that's probably acceptable on the front end. On the sorts of machines that Rob was talking about, the ML machines, traditionally HPC and ML machines have worked in a model of you're either 100% there or you're not in the game because of the bulk synchronized way that the applications work. So that may be more of an issue if we wanted to apply that model to a back-end network. And, you know, I think we all kind of feel that this is the way that we're going, and very much this is an issue of not if, but when. And the driving factor on the when is really the TCO, is primarily TCO, but a much more complex measure of TCO than just CapEx and OpEx. So TCO expanding to think about how does it change your deployment model? Does it take you longer to roll things out in this space? And how does it change your repair and your sparing models? And just to sort of wrap with a couple of examples of how that might play, well, in immersion cooling, potentially the ability to go optics to the machine actually will give us a benefit in terms of overall system TCO. So today we've got a kind of an issue that we've got potentially a mismatch between the radix of the switches and the number of endpoints that you can actually land in a tank. So the lovely advantage of getting the flexibility of fiber to the machine is that we completely decouple the number of machines in the tank from the radix of the switches. There's a kind of secondary advantage in that we're freeing a bit more of that valuable tank space for more CPUs in there. Gives us, in terms of the transition into immersion cooling, it gives us a little bit of an advantage because we don't have to think about immersion cooling the switches first off. We just use them around the compute nodes. But ultimately, immersion cooling is potentially interesting for for our optics and for our switches. And there's some nice things to think about there because some of the characteristics of optics are very well aligned with immersion cooling in that in the immersion cooled systems, fail in place becomes a lot more important because we don't want to be lifting the lid on the tank all the time. And similarly with these large co-packaged switches, that's going to be a motivator for fail in place. So one way in the other direction where we can look at other changes in the optics space which would really help us in terms of being able to deploy optics more widely. A huge concern from our deployment people is that if we go to taking optics to last tier, that's probably three times as many optical connections. So there's a concern about how quickly can we roll out and install all those optical links. One thing we've been experimenting with in Microsoft is expanded beam optics. And we're seeing really, because our normal optics deployment, we would expect someone to clean and fit it. And we don't know whether they actually do it because some of them curiously seem to have a fair bit of dirt in them. But a much better way to go about it is to say, well, let's build a connector which doesn't actually need that clean step. And we've actually deployed some clusters using expanded beam optics and found very good results in terms of you can hook these more tolerant optical connections up as easily as if they were copper connections. And that way we kind of redress the potential impact on TCO of saying you're going to slow down deployment. And actually slowing down deployment of machines is a really big TCO hit for us if you're stacking things back through the manufacturing cycle. Yep. So good timing, despite a shaky start. We're tantalizingly close to the optical data center. It's very much a question of when, not if. The decision of when we actually get to that point is very much TCO driven, but that's by a much, much wider definition of TCO than our current way of looking at it, which tends to focus very specifically on power and CapEx. Thanks.